Hello, I'm Maruk Said, your microbiology guide. Let's explore in-depth micro techniques and uncover groundbreaking insight together on this educational journey into the fascinating realms of microbes.
FTIR Spectroscopy and Graph Plotting Tutorial. Table of Contents. Introduction to FTIR. Why FTIR? Principle of FTIR. Instrumentation of FTIR. Advantages of FTIR. Applications of FTIR. Limitations of FTIR. Understanding FTIR graphs. Why plot FTIR data in Origin software? Introduction to FTIR. Fourier Transform. Infrared spectroscopy is the preferred method of infrared spectroscopy. In infrared spectroscopy, IR radiation is transmitted through a sample. The sample absorbs some of the infrared energy, while some of it passes through. The resulting spectrum provides a molecular fingerprint of the sample by showing its absorption and transmission characteristics. Each unique molecular configuration produces a distinct infrared spectrum, much like human fingerprints. This uniqueness makes infrared spectroscopy valuable for a wide range of analyses. FTIR spectrometers are widely used in fields such as organic synthesis, polymer science, petrochemical engineering, the pharmaceutical industry, and food analysis. FTIR spectrometers can also be hyphenated with chromatography, allowing them to be used in studying chemical reaction mechanisms and detecting unstable compounds. If you have watched till here, don't forget to subscribe to Family of Science Lovers. Press the bell icon button so you are always updated. Why FTIR? Infrared spectroscopy has been a reliable technique for material analysis in laboratories for nearly 70 years. An infrared spectrum acts as a fingerprint for a sample, where absorption peaks represent the vibrational frequencies of atomic bonds within the material. Each material has a unique atomic composition, so no two compounds produce the same infrared spectrum. This uniqueness allows infrared spectroscopy to provide positive identification, qualitative analysis, of any material. The peak magnitudes in the spectrum indicate how much of the material is present, enabling quantitative analysis when combined with modern software algorithms. Fourier Transform. Infrared spectrometry addresses the limitations of traditional dispersive instruments, especially the time-consuming scanning process. FTIR allows simultaneous measurement of all IR frequencies using an optical device called an interferometer, which embeds all IR frequencies into a single signal. The signal is typically captured within a few seconds, making the process very fast. Most interferometers include a beam splitter that divides the incoming infrared beam into two paths, one fixed and one variable due to a moving mirror. The interference between these two beams produces a signal called an interferogram, which captures all frequencies at once. Since the interferogram cannot be interpreted directly, a mathematical technique called Fourier transformation is used to decode it into a usable frequency spectrum. FTIR spectroscopy is preferred over dispersive or filter methods for several reasons. It is non-destructive. It offers accurate measurements without needing external calibration. It allows fast scanning, collecting a scan every second. It enhances sensitivity by averaging multiple scans to reduce random noise. It provides higher optical throughput. It features a simplified mechanical design with only one moving part. Principle of FTIR. The principle of FTIR is based on the use of a Michelson interferometer. The Michelson interferometer consists of three main components: a beam splitter, a moving mirror, and a stationary, fixed mirror. The beam splitter divides the incoming light beam into two separate beams. One beam reflects off the stationary mirror, while the other reflects off the moving mirror. These two beams are then recombined by the beam splitter. As the moving mirror moves back and forth, reciprocating motion, the optical path length of the beam reflected from it changes. This variation in path length leads to a continuous change in the phase difference between the two beams. When the two beams recombine, their phase differences cause constructive and destructive interference, producing an interference pattern. This pattern of interference light is detected and recorded as an interferogram. The interferogram represents the intensity of the combined light beams, with the optical path difference plotted along the horizontal axis. Instrumentation of FTIR. FTIR instrumentation includes several key components that work together to generate and analyze infrared spectra. The source. A broadband emitter provides the IR radiation. Common sources include mid-infrared ceramic sources, far-infrared mercury lamps, near-infrared halogen lamps. The interferometer. The core of an FTIR spectrometer, composed of a beam splitter, semi-transparent mirror that divides a collimated light beam into two optical paths, a stationary mirror, a moving mirror. Half of the light is transmitted to the moving mirror, and the other half is reflected to the stationary mirror. Both mirrors reflect the light beams, which then recombine at the beam splitter before entering the sample chamber and reaching the detector. The sample. The recombined beam enters the sample compartment. Depending on the analysis type, light is either transmitted through or reflected from the sample's surface. The sample absorbs specific frequencies of infrared energy that are characteristic of its molecular structure. Detector measures and converts the transmitted or reflected light into an electrical signal. The detector's material and design determine the sensitivity and range of data that can be captured. The detector first converts the IR beam into photons, which are then converted into electrical signals readable by a computer. Common detectors include room temperature, deuterated L-alanine doped triglycine sulfate for standard applications, cooled liquid nitrogen detectors for high-sensitivity applications, silicon photodiodes for near-infrared and visible IR applications, silicon far-infrared bolometers for far-infrared range analysis. Advantages of FTIR. FTIR has higher speed because all frequencies are detected simultaneously, allowing most measurements to be completed within seconds. This is known as the Felget advantage. It offers high sensitivity due to multiple factors. More sensitive detectors are used. Greater optical throughput reduces noise levels. Fast scanning allows multiple scans to be added together, co-added, to reduce random measurement noise to any desired level. FTIR provides high accuracy and reproducibility, making it well-suited for background subtraction. It is a highly reliable technique for positively identifying nearly any material. Instruments include a He-Ni laser for internal wavelength calibration, known as the Con Advantage. This allows for self-calibration, eliminating the need for manual user calibration. FTIR can capture IR data from very small sample sizes. It has high optical throughput, referred to as the Jacquinot advantage, meaning the radiant power reaching the detector is significantly higher than in dispersive instruments. FTIR delivers high precision as the laser functions as a stable reference signal and timekeeper. Internal synchronization ensures reliable results, unaffected by external factors, like sunlight or temperature changes. Applications of FTIR. FTIR spectroscopy is widely used to analyze industrially manufactured materials during quality control processes. It serves as a common first step in material analysis by detecting changes in absorption, band patterns, indicating alterations in material composition or contamination. It is employed in drying processes for polymers, photoresist materials, and polyimides. FTIR investigates the interaction between matter and electromagnetic radiation, producing a spectrum for analysis. FTIR spectrum analysis aids in diagnosing various organ diseases and quantifying biomolecules like proteins, nucleic acids, and lipids. It is a valuable method for assessing fuel stability variations in biodiesel antioxidant mixtures. In failure analysis, FTIR helps detect breakdowns, oxidation, and the presence of uncured monomers. FTIR is used in high-resolution experiments. It supports trace analysis of raw materials and final products. It enables analysis of reactions occurring on the microsecond time scale. It is used for analyzing chromatographic and thermogravimetric sample fractions. FTIR identifies reaction components and is useful in kinetic studies of chemical reactions. It aids in compound identification by comparing the unknown substance's spectrum with reference spectra. Fingerprinting. FTIR is used for identifying functional groups in unknown compounds, such as ketones, aldehydes, carboxylic acids, and more. Limitations of FTIR. The molecule must be infrared active. At least one vibrational motion must change the molecule's net dipole moment when exposed to IR radiation for absorption to be detected. FTIR provides minimal elemental information for most samples, making it less suitable for detailed elemental analysis. The material being analyzed must be transparent in the spectral region of interest. Opaque or highly absorbing materials can hinder accurate measurements. If you have watched till here, don't forget to subscribe to Family of Science Lovers. Press the bell icon button so you are always updated. Understanding FTIR graphs. What does an FTIR graph show? The FTIR spectrum is a graph of infrared light absorption, or transmittance, versus wave number per centimeter. Each peak represents a specific vibrational mode of a chemical bond, helps to identify functional groups, and assess molecular structure. Axis details. X-axis. Wave number per centimeter. Ranges from 4,000 to 400 centimeters to the inch. Higher wave numbers equals stronger bonds, or lighter atoms. Lower wave numbers equals heavier bonds. Y-axis. Usually percent transmittance or absorbance transmittance. How much IR light passed through absorbance? How much was absorbed by sample? Important regions. Functional group region, 4,000 to 1,500 Cs to the power of -1. Most diagnostic bands for identifying functional groups. Fingerprint region, 1,500 to 400 centimeters to the power of -1. highly specific to individual molecules, used for compound identification through spectral matching. Common peaks to recognize. OH stretch, broad, approximately 3,200 to 3,600 cm to the power of -1. C equals O stretch, sharp, approximately 1,700 reciprocal centimeters per second. C to H stretch, 2,800 to 3,000 centimeters to the power of -1. NH stretch, 3,300 to 3,500 reciprocal centimeters. CO stretch, approximately 1,000 to 1,300 centimeters to the power of -1. Interpretation tips. Sharpness, intensity, and shape of peaks matter. Compare experimental spectrum with standard reference spectra. Use peak position, width, and height to deduce molecular structure. Why plot FTIR data in Origin software? Advantages of using Origin. Professional high-resolution plots for research or publication. Allows custom labeling, color schemes, and peak annotation. Easy to zoom into specific regions, e.g., fingerprint region. Key features for FTIR plotting. Import FTIR data directly from Excel or CSV files. Customize axes. Reverse x-axis, standard for wave number. Add vertical lines to mark important peaks. Overlay multiple spectra, e.g., control versus treated sample. Use baseline correction and peak deconvolution tools. Organize and save. Save your project with multiple graphs in different folders. Reuse templates for similar spectra. Export high-quality figures, JPG, PNG, TIFF, PDF for papers. Enhanced data presentation. Add titles, legends, sample IDs to make it viewer-friendly. Use color coding for time course or concentration-based studies. Highlight degraded, shifted, or new peaks for biodegradation analysis. Welcome to this FTIR graph plotting tutorial using Origin software. Let's begin by opening the Origin software. Once you're on the dashboard, click Project, then Save Project As, and name your project based on your work. Now, pin the Project Explorer for easy access. Start organizing your workspace by creating folders, one for each sample. This will keep your data clean and separate. Also, create a combined folder where you'll stack all sample data for comparison later. Open any one of your folders to begin. Now go to Data. Click Import from File, then Import Wizard. Click the three dots to browse your computer and open your saved FTIR file. Click OK, then Finish. Your raw data is now displayed. You may notice background noise or uneven baselines. That's normal. We'll now begin refining this data. First, name your axes. The x-axis should be wave number in reciprocal centimeters, and the y-axis should be transmittance in percent. Select all your data and click the line graph icon to generate your plot. Now, Step 1, Baseline Correction. Click Analysis, then Peaks and Baseline, and choose Create Baseline. In the dialog box, keep clicking Next until you reach the Modify Baseline step. Double-click on the graph to add baseline points. Position these along the curve where the baseline should lie. Once done, click Subtract, then Finish. Next, go to Analysis, click Mathematics, and select Subtract Reference Data. In the dialog box, choose Baseline Plot 2 as the reference and click OK. Head back to your worksheet, select Wave Number and Subtracted Data, and plot the corrected graph. Your baseline is now corrected. Next, Step 2, Smoothing the graph. Click Analysis, go to Signal Processing, then click Smooth. Set the window size to 20 points. This helps retain minor peaks, especially in the fingerprint region. Click OK. Then go to your worksheet and plot the smoothed data using wave number and the smooth column. Step 3, Peak Identification. Go to Analysis, then Peaks and Baseline, and select Peak Analyzer. Choose Find Peaks and keep clicking. Next until you reach the Find button. Click Find to detect peaks automatically. To refine, turn off AutoFind and manually add or delete peaks. Click Peak Info to deselect unnecessary peaks, then click Finish. Now let's refine the graph layout. Delete the old raw line if needed. Set the x-axis scale to 4,000 to 400 centimeters per second squared. Clean up unused axes and rename them clearly. Use the Insert menu to add borders and straight lines. Label peaks with arrows and text boxes for clarity. For precision, insert vertical lines and annotate major peaks. Finally, exporting your graph. Click File, then Export Graphs. Select your desired format, such as PNG. Choose the destination folder, name your file, and click OK. Your FTIR graph is now saved and ready to use. And that's how you process and plot FTIR data using Origin, step by step. Thank you so much for watching. Don't forget to subscribe to my channel, press the bell icon button. Thank you.